Hey, so this worksheet is called 42 in class. No, sorry, 44 in class volumes practice. I don't know if you're going to do it or not, but just in case, I thought I would have the video for you to check your answers. Problems 1 through 8, set up but do not evaluate the following integrals. Okay, I think that's fabulous. I really like this. 1. Y equals square root of x minus 1 on 1 to 2. Okay, so this is our square root graph shifted right 1. And so we're looking at that. 1, 2, 2, 1. This is our region. Okay, I want to go about the x-axis with disks. So there's my radius. The r is the y value. And remember, we're integrating area. So this is going to be pi. Radius is y squared. But wait a second, the thickness of this disk is a dx. So I got to get rid of that y and replace with some x stuff. So from 1 to 2, pi square root of x minus 1 squared dx. And you could certainly write pi 1 to 2 x minus 1 dx. Okay? But it does say just setup, and this would be a fine setup. Okay. Part B, same thing with shells. Okay, so we've got this function, square root of x, and I want to rotate around the x-axis, but this time I want shells. So I'm going to draw something that is parallel to the axis of symmetry and draw my circles. Well, I can see that the radius is that y value. And that's fine this time because my thickness of the shell is going to be measured here on my y-axis. Nice, it's a vertical distance. But what about the height? Well, yeah, the height is changing, isn't it? So it's this number minus this amount. Like, so it's 2 minus x will give me that length. So h equals 2 minus x. However, this is a dy integral, and so I'm going to have to get rid of this x and replace with some y stuff. So our function, x minus 1 equals y, I get x minus 1 equals y squared, and so x equals y squared plus 1. So my height is 2 minus y squared plus 1, or h is minus y squared plus 1. So then my integral, and this is dy, so I'm going from 0 to, what's the y value here at 2? 2 minus 1 is 1, square root of 1 is 1. Okay, so I'm going from 0 to 1 of 2 pi. The height is 1 minus y squared, and the radius, remember, was that y value, y value. Oh yeah, just the y value. Sorry, dy. Okay, and you can always check your thoughts by doing the other method and seeing if you get the same answer both times. That's what we're looking for here. Okay. Problem number 2 takes the same region, but this time we're looking about y equals 1. Okay. So here's y equals 1. And that's what we're rotating around. And we're taking this region, and first we want to do washers. So washers, I draw something that's perpendicular to the axis of rotation. At each end, I draw a circle whose center is the axis of rotation. I see that my big R, no matter where I draw this segment, my big R stays the same. It's bounded here. So we could do top minus bottom. But little r is changing. I know that this amount is y. I know that this amount is 1. And so that little r is going to be 1 minus y. However, this is a vertical slice. See that dx change? Since this is a dx integral, I need to get rid of that y and replace with some x stuff. So my integral, well, I'm going to be integrating from 1 to 2, and I'm going to have big R squared minus little r squared dx. And then don't forget that pi. Okay, now what if we look at the same problem, but this time we considered using shells. Okay. So I've got this shape, I've got this, oops, not there. I've got this line that I'm rotating about, and I want to do shells. So if I'm doing shells, I know drawing something parallel to the axis of rotation is what's called for. And so my radius is this distance. Well, this distance is called y, and this distance is 1. So my radius is going to be 1 minus y. But what about my height? Well, this is x, and this is 2. So my height is going to be 2 minus x. But we're not allowed to have x in a dy integral, so I want to find out what x equals. Well, remember that y was the square root of x minus 1, so y squared plus 1 is x. So h is 2 minus y squared plus 1. Or, if we tidy things up, h is 1 minus y squared. So then my integral is going to go from 0 to 1. It's 2 pi. The radius is 1 minus y. And the height is 1 minus y squared dy. All right, here's problem number 2. How about problem number 3? Same region, this time around x equals 2. X equals 2. Okay. There's 2. This is x equals 2. And we're starting with disks. So I draw something perpendicular to the axis of rotation. There's my circular disk. I expect a disk instead of a washer because my region is lined up along the axis of rotation. This is called x. This is called 1. So my radius is 1 minus x. However, these are dy slices. So I've got to get rid of that x and put in some y stuff. Wasn't it the case that we had 1 minus y squared for x in the last problem? I think so. So I can get rid of this by replacing all this stuff here. Well, let's just check that. So square root of x minus 1 equals y. Yeah, y squared plus 1. It's not the same. Okay, so not that. I'm glad I checked. So x is equal to that. I have 1 minus y squared plus 1. The 1's are going to cancel, and I just get minus y squared as the radius. That seems strange and uncomfortable. This is 1, this is x, that's my radius. Yeah, 1 minus x. Okay, so the integral then that I would be looking at would be pi. Now remember, we're integrating dy here, so we're going to go from y equals 0 to y equals 1. And my radius is minus y squared. That doesn't make any sense to me whatsoever. But I'm squaring it, so it'll just be y to the 4th. Yeah, let's think about that just one more time. So that is 1 minus x, and x is y squared plus 1. Let's distribute. Yeah, that's perfect. Okay, So there's my setup with washers. What about shells? So if I'm doing this region with shells around x equals 2, draw something parallel to the axis of rotation. Oops. Okay, so it looks like the height is the y value there. H equals y, or square root of x minus 1. And the radius, well, this is 1, this is x, and so the radius is 1 minus x. Okay. And this is a dx integral, so we're going from 1 to 2. Don't lose that 2 pi. 1 minus x, square root of x minus 1 dx. That would be my write-up for problem number 3. Problem number 4 has us rotating about y equals 3. Okay. So we've got something like that. And we're asked to do this both as washers and as shells. So with washers, I write something perpendicular to the axis of rotation. I know that this distance is 3. I know that that distance is y. So it looks like my little r is going to be 3 minus y, or 3 minus square root of x minus 1. Okay, and what about big R? Well, big R seems to be just a constant, top minus bottom. Big R is 3. So my integral would be, going from 1 to 2, pi big R squared minus little r squared dx. No, I'm not going to simplify it. No, it just says right up an integral. So what about the second one? The second one has us doing this again, but this time we're doing shells. Since we're doing shells, I want something that's parallel to the axis of rotation. And so there I go. Now I see this distance is y, this distance is 3, and so my radius is 3 minus y. And I like having y there because this is a dy shell. So what about the height? Well, the height's a little trickier. Here's the height here. Now we know that this is x, and this is 2. Oh, I might have missed that on the previous problem. I might have said 1 then, so if I did, I'm sorry. So 2 minus x. Great, but we want to do y, so we're going to have to get rid of this x. And do 2 minus y squared plus 1. So 2 pi integral 0 to 1, going from here to here. Our height is 2 minus y squared minus 1, which will just be 1 minus y squared, and then times that radius, 3 minus y. Okay. So that's problem number 4. 5 has us going same region, but this time around x equals 4. Okay, so with washers, draw something that's perpendicular to the axis of rotation, and then at each end of that segment, I'm going to draw a circle whose center is the axis of rotation. Well, this little r is always going to be bounded by this and by this. So little r is 4 minus 2, or 2. But what about big R? Big R goes from here to here. It is bigger. So this is x, this is 4. Therefore, my big R is going to be 4 minus x, which is the same as 4 minus y squared plus 1. So if I combine like terms, r equals 3 minus y squared. So my integral here then would be pi, and it's dy, so we're going from 0 to 1. Big R is 3 minus y squared squared minus little r, 2 squared dy. And I think that's my setup. That's always 2 minus 1. Sorry, that's a 4. 2 minus a 4 minus 2. Good. And then this one, this is 4. This is x. That's x. Distribute, combine my terms. Yeah, I'm going with that. Okay, so there's 5 done with washers. What about 5 done with shells? Y equals negative 1 is what we're rotating around. So there's my region. Here's y equals negative. Whoa. No. Come on, you didn't do the second one with number 5. Okay, so I've got this, and I'm rotating over here. But this time I'm using shells. Okay, cylindrical shells. So h is my y value, which is square root of x minus 1. R, well, this is r. This is x, and that is 4. So 4 minus x, however, this is a dx integral. I like that, I like that. Hey, I'm good to go. 2 pi. Remember, we're integrating from here to here. We're only integrating the region. Not going up to 4, not starting at 0. We're just doing 1 to 2. 4 minus x times square root of x minus 1 dx. Fabulous. So there's the rest of number 5. Now, about number 6. So number 6 wants us to go around y equals negative 1. And if I think about disks and washers and draw something perpendicular to the axis of rotation, and I get that. Well, I think this distance is going to be a constant 1. 0 minus a minus 1 is 1. And that's my little r. My big R, using top minus bottom, my big R is going to be y minus a minus 1 or y plus 1. Now I do notice that these slices have a dx thickness to them. So I don't want to have that. Instead, I want square root of x minus 1 plus 1. Okay, so my integral then, and these are x things, right? Are they x things or are they y things? These are x things. I need x values, so I'm going from 1 to 2. And I want pi, big R, square root of x minus 1 plus 1 squared minus little r dx. Okay, but what happens if we consider this situation with shells? Okay, same shape, rotating around here. I draw something that is parallel to the axis of rotation. So the radius looks like the y value and then to the axis of rotation, which is negative 1. So I'm going to have y minus minus 1 or y plus 1 for the radius. And that's a dy shell, so I'm happy with that. But what about the height? Well, the height. This is the height. It's a changing quantity. This amount is x. This amount is 2. So I know the height is 2 minus x, but since we've got a dy integral, I'm going to get rid of this x and replace that with y squared plus 1. When I combine like terms, I get 1 minus y squared for my height. And so in this situation, my integral, and by the way, it's y's, so I'm going from 0 to 1, 0 to 1, 2 pi. The radius is y plus 1, and the height is 1 minus y squared dy. Ta-da! Okay. 6. There's our region. Oh, that was 6, and I did that with shells as well. I did washers. Shells. Yes, I did shells. I think. Maybe not. Okay. 6 with shells. So h equals y, or square root of x minus 1. And radius. Well, this is x. This is 4. R equals 4 minus x. So 2 pi, 1 to 2, 4 minus x, square root x minus 1, dx. Okay, I think we're all set there. Now, number 7. This time we have a footprint with squares perpendicular to the x-axis. So I'm drawing in squares. Well, I know I'm integrating area, which in this case is sides squared. And I notice that s is my y value for an ordered pair here. Okay, this is definitely intersecting the x-axis is the dx thickness, so I want x minus 1 here. But we want s squared, so s squared will be y squared or x minus 1. Cool. So I'm going to integrate from 1 to 2, x minus 1, and that's squared already, dx. There we go, all done. I should actually do this then. X squared over 2 minus x from 1 to 2. Now we plugged in so many zeros in this unit that a lot of people just plug in this number, and that would be a mistake. If for no other reason then, 2 squared is 4, 4 divided by 2 is 2, and 2 minus 2 is 0. Right. We know this thing is going to have a volume. So let's actually plug both numbers in. Okay, so we have 2 minus 2 minus, now I'm plugging in a 1. 1/2 minus 1. So that's 0 minus negative 1/2, or positive 1/2 units cubed. Okay, now we want cross sections perpendicular to the y-axis. Same region, but now I'm drawing squares like that. And again, I'm integrating area. So I'm integrating sides squared. This time, the thickness is a dy thickness. And so I want to integrate from this y value to this y value. And that's going to be from 0 to 1. Now, s is this amount. This is x, and this is 2. So we can say that s equals 2 minus x. However, we have a dy integral. So 2 minus, and what was x equal to? X was equal to y squared plus 1. So I'm going to end up with 1 minus y squared as s. And we want to integrate s squared, so 1 minus y squared squared dy from 0 to 1. I believe that's good. 2 minus x, distribute, combine, and we're just squaring that amount. That seems fabulous. Okay, so this is going to be integral from 0 to 1 of 1 minus 2y squared plus y to the 4th. And when we do the antiderivative, we're going to have y minus 2/3 y to the 3rd plus y to the 5th over 5 from 0 to 1. Okay, so here if I plug in 0, yes, all of those go away. So when I plug in 1, 1/5. Okay, make a common denominator of 15ths. And I end up with 8 over 15 units cubed. Alrighty, that's 8. What about 9? 9 says you've got this thing. Ugh. Yeah, I have no idea what that thing looks like. My guess is that I need to pull out my calculator because I don't know what x to the third plus x plus 1 looks like. Okay, x to the third plus x plus 1. And I just want to see what that looks like on 0 to 1. Okay, 0 to 1. And the y values. If I plug in a 0, I get 1. If I plug in a 1, I get 3. So I'm going from 0 to 3. And graph. Okay. So I'm looking at this kind of thing. This is y equals x to the third plus x plus 1. Here's y equals 0. Here's x equals 0. Here's x equals 1. So this is the region we're talking about. Okay, is rotated about the y-axis. Explain whether you prefer to use discs or washers or shell, and why in each case. Set up, but do not evaluate. Well, so here's the thing. This is very clearly, to me, a shell problem. Why? Because even though this distance is the same, and it's always going to be 1, this is changing. First, I have 0, and then I have that cubic. So if I'm trying to do something like washers or discs, like this bottom would be discs and this top part would be washers, I'd have to set up 2 different integrals to do that. That would be the integral from 0 to 1, because that's where that is, because when I plug in zeros, I get 1. And I'm just going to have circular disks in that case, so I just need to know that radius is my x value. Oh, wait. How do I solve that equation for x? Guess what? Algebraically, it's impossible. I can't solve that for x. So there's no way I can do disks and washers here. Yeah, so give it up. Instead, we're going to do shells. Parallel to the axis of rotation. I see that h is my y value, also known as x to the third plus x plus 1. And this radius is x. So we're just going to integrate 2 pi. We're going from here to here of x times x to the third plus x plus 1 dx. Wow, that's so much faster. Yeah, so think about it. It's 2 different, like here's a little r, and this is just an r because this is just a circular disk here up to 1, and then from 1 to 3, because that point there is 1 comma 3. To go from a y value of 1 to a y value of 3, I need washers. I have this outer radius of 1 and this inner radius as 1 minus x. And then I still have to get rid of that x and replace it with some y stuff because that's a dy. Yeah, I don't want to do that. So instead, I'm moving on to problem number 10. This is the last problem here. How would you find the volume generated by rotating the region bounded by 16 minus x squared? That's 4. That's 2. And the x-axis. X-axis? Y equals 2. Curve. And the x, no, that's gotta be a typo. That's a semicircle. That's y equals 2. Oh. That's my region and I'm going around the x-axis. Gotcha. Okay, well, I definitely don't want to do, well, I don't want to do, but not definitely. You know, if I were doing shells, I'd have this, and I would say, okay, my radius is this y value here. And that's good. The height, however, the height is going to be this, which is square root of 16 minus x squared. And over here, we have, it's not negative. Yeah, that's awkward. See, they're same. You know, I want to say though that actually this distance is x, and this distance must also be x. So here my height is 2x. This is a dy, so I would need to solve this equation for x. Y squared equals 16 minus x squared. X squared equals 16 minus y squared. X equals square root of 16 minus y squared. Okay. So I think I could do the 2 pi y times square root 16 minus y squared dy. And where are we integrating from and to? Well, we're integrating from this line, y equals 2, up to here, y equals 4. So that might be my setup if I wanted to do shells. I think washers is easier. Let's take a look. Okay. That's y equals 2. There's our square root of 16 minus x squared. And we're going around x-axis. Okay, and it looks like these radii are the same. Little r is 2 minus 0, so little r is 2 at the top minus bottom there. But what about big R? Big R, that radius is in fact the y value to that point. Huh. So big R is going to be the y value, which in this problem is square root of 16 minus x squared. So my integral, pi, big R, 16 minus x squared, square root squared, minus little r squared dx. And where are we integrating from and to? Well, not 0 to, I don't know where that x value is. So 2 equals 16 minus x squared, because I'm looking for the point of intersection for these. And I get x squared equals 14. And so this is going to be square root of 14, negative root 14. Okay, I mean, I guess you could always do something like 0 and double it, because this volume and this volume will be the same. That might be easier to evaluate with. Do we need to actually calculate this? How would you find? Well, I think I would prefer washers. And of course, we should get the same answer for both of these, though it's a little concerning. Really? Somehow we're going to get the same answer? Shells, I expect, oh, that too is because I didn't go negative root 14 to root 14. Okay. From this x value to this x value. Where those x values, we set the horizontal line equal to the semicircle. That's what this is. Squared both sides. Oh, did I square both sides? No. Yeah, wait a second. Wait a second. So this is 2 equals square root 16 minus x squared. Oh yeah, we need to square both sides. 16 minus x squared. X squared equals 12. Okay. So plus and minus 2 root 3. That feels a little better. And you could certainly tidy this up. this square root and square root undo each other. This is going to be 4. 16 minus 4 is 12 minus x squared. So we could get rid of all of that and say 12 minus x squared. Okay. Yeah, I don't know. Whichever one you want. But number 9, yeah, no freaking way that I'm going to be able to do that with disks because I can't solve that polynomial at cubic 4x equals. All right, well, I hope this was helpful for you. Have a fabulous day. Take care.